Good evening, everyone. Welcome to this tutorial lecture on problem solving session for social networks. So this week we'll be discussing week 6 questions from previous iteration of this course, and tomorrow week 7 questions will be discussed. So I'll start sharing my screen. All right. So uh, let us get started with today's session. So coming to question 1, if nx represents a network X library, then for a graph G, what does nx dot PageRank of G returns? So you have four options: returns a list of page ranks of the node, returns a dictionary where keys are nodes and values are page ranks, returns a list of nodes sorted in ascending order of page rank, and returns a dictionary where keys are page rank and values are list of nodes with the same page rank. So the right answer for this question is option B, where let's say you have a graph like this. So consider a directed graph. So this is your directed graph G. So what nx dot page rank of G returns is a dictionary. And let's say the keys are the node. So let this node be 0, this node be 1, this node be 2, this node be 3. So it would return something like 0 and would return page rank of 0, 1 page rank of 1, 2 page rank of 2, 3 page rank of 3. So this is the format in which this function returns. So the right answer for this question is option B. Okay, so moving on to the next question. A web graph is, you have four options: a complete graph, an undirected graph, a directed graph, a bipartite graph. So if you look at a web graph, let's say web graph is basically a web graph is collection of web pages, and the edge in a web graph denotes link from one web page to another. So you basically have, let's say this is your graph, web page. So for simplicity, let us consider only four web pages. So these web pages are the nodes in a web graph, and the edges are the links, the hyperlink that takes from one web page to another. So it could be something like this. So if there is a link, so web page 1, there is a link to web page 2, but this does not mean that there is a link from web page 2 back to web page 1. So this is not guaranteed. So if there is a link from web page 1 to web page 2, it doesn't mean that a link also exists back from web page to web page 1. So therefore, this web graph is directed. The right answer is option C, is a directed graph. Moving on to the next question. Okay, let us consider question 3. So let there exist n nodes with no edges in between them initially. We start moving from one node to the another. Probability of moving from one node to any other node being the same and creating an edge between the nodes if there already isn't. After a large number of iterations, the graph generated will be. So what they are basically saying is that uh, it will, suppose you have these nodes, say 6 nodes. So what you do is start from one node, and with equal probability you hop on to any other node. So let's say you hop on to here. From here you can hop to here. From here you go to here. From here you can go back here. And let's say from here you go here. From here you can go here, and like this. So if it is saying that if you do this for a large number of time, a large number of iterations, so the graph generated will be, so you have two four options: bipartite, connected, acyclic, or complete. So if you see, if you keep repeating this process, and from every node you can jump to every other node, so eventually what will happen, that every node will hop on to every other node. So there will always exist an edge from every node to every other node, which makes it a complete graph. And since it is complete, it will also be a connected graph. So it would be a fully connected graph, and the correct answer is only 2 and 4. So it's connected and complete as well. Is there any questions so far? Uh, all right, then let us move on to the next question. So coming to the next question, so Google PageRank algorithm uses, we have four options: a dictionary of web pages created manually by Google workers, list of pages relevant to the search, and rank those pages based on the creation date, web graph and searching algorithms like depth first search, web graph, and random walk algorithm. So the PageRank algorithm, the right answer is option D, web graph and random walk. It is, so this is how they collect the web graph. So it randomly visits any node. So this randomly will visits the web page, and from there it hops on to another web page via the hyperlinks present on the web page, and it carries on like this. So so that is how the web graph is being collected. So from web page one web page randomly selected based on keyword search, it does a random walk and visit other web pages via the hyperlinks. And after uh, uh, many iterations, it it gets covers the complete graph, the entire graph, and ranks the nodes as well. So that is how the PageRank algorithm works. So if it would be impossible to maintain a dictionary of web pages, so it just starts with any web page at random based on the keyword you give in the search, and from there it does a random walk, finds neighboring web pages via the hyperlinks, and eventually it covers the entire graph and then ranks the nodes, and that gives you the page rank. Okay. Coming to question 5. Choose the correct option based on the two statements given below. So statement 1 is page rank of a node depends only on its out degree, and statement 2, page rank of a node A can be higher than node B even if fewer nodes have an edge going to A compared to node B. So in a so out degree and out degree or in degree and page rank, they have no correlation. So it if a web page has a higher out degree, it doesn't mean that it also has a higher page rank, and similarly if it has a lower out degree, it doesn't mean it has a lower page rank. So there has been no correlation found between out degree or in degree of a node with page rank. So definitely statement 1 is not correct. Statement 2 says that page rank of a node A can be higher than that of node B even if fewer uh, nodes have an edge going to A compared to B. So let us consider node A and node B. So there can be many nodes going to B, and it's only a few going to A. But it can happen that the nodes going to A, nodes going towards A, they themselves might have lots of nodes coming in. So which eventually will make the page rank of A very high compared to B. So B may have higher number of edges going towards it, but the uh, nodes which lead to B may not in themselves have very many may not be may not have very high page rank. So it could be something like this. So in a situation like this, the page rank of A will be greater than page rank of B. So option 2 can be correct. So the right answer is option 1 is incorrect and option statement 2 is correct. Okay. Moving on to the next question, question 6. So the initial page rank of each node in this directed graph is 1 by 4. What will be the page rank after one iteration? So the page rank was initially 1 by 4. So let us draw it. Okay. So you have A. So initially everyone had page rank 4. So basically, if you look at the option, they are asking us to find the page rank of B and C after one iteration. So, so if you look at page rank of B, after one iteration, it it gives away its 1/4 entirely to D, but receives something from A and something from C. So it receives from A and it receives from C. From A, what it receives is half of 1/4. So A distributes to B and C. So that is how 1/4 of A is being split between between B and C. So B gets half of 1/4, and from C has only one outgoing edge, and C gives its entire 1/4 to B. So the right answer would be, so 1/8 plus 1/4, that would be 3/8. So the page rank of B is 3/8. Now page rank of C. So C receives only from A. So it does, there is only one edge that gets into C. There is one incoming edge, and that is from A. So the page rank of C would basically be half of the page rank of A. So half of 1/4. So that is 1/8. So the right answer is 3/8 and 1/8, option A. Is this clear? If you have any doubt, you can ask, or you can ask at the end as well. Okay, let us move on to the next question. So coming to the next question, below is the adjacency matrix for a graph. X, Y are the page ranks of node 2 and 3. And after two iterations, Z is equal to X by Y. So initial page rank is 1 by 4. So what is the value of Z? So the nodes are numbered like this. So node 0, node 1, node 2, and node 3. So basically we'll have to find out what is the page rank of 2 and what is the page rank of 3. And then we'll be able to find out what is Z. So if you, what is an adjacency matrix is, adjacency matrix, it gives you the, gives the structure of the graph. Aij equal to 1 if edge exists from I to j and aij equal to 0 if no edge exists from I to j. So in this adjacency matrix, so let us draw this graph that they have shown via the adjacency matrix. So let us draw 4 nodes. So you have 0, you have 1, you have 2, and you have 3. So it says that node 0, there is an edge from node 0 to node 1. There is a edge from node 0 to node 3. For node 1, there is an edge from 1 to 2 and 1 to 3. And for node 2, there is one edge going to node 0, and there is one for node 3, there is one edge going to node 2. Okay. So this is the structure of the graph that you get from this adjacency matrix. Now let us try to find its uh, the page rank after 2 iterations. So so let us write it like this. So iteration 0, you have node 0, 1, 2, and 3. Iteration 1, iteration 2. So you have node 0, 1, 2, and 3. You have 0, 1, 2, and 3. So initially all the nodes had 1/4. In iteration 1, what happens is node 0 distributes its page rank to node 3 and node 1, but it gets back from node 2. So node 2 had 1/4. So this is iteration 1. So node 2 had 1/4, 1/4, 1, 1. So node 0 gives its divides its 1/4 equally between node 1 and 3. However, node 2 gives its entire 1/4 to node 0 because it has no other outgoing edge. There is only one outgoing edge from 2 to 0. So 1/4 goes directly to 0. So page rank of uh, node 0 would be 1/4. Coming to node 1 uh, has one incoming edge and two outgoing edge. So in the one incoming edge, so outgoing edge would take away the already existing page rank and distribute it to its neighbor. So the page rank of 1 was initially 1/4 and it was equally distributed between 3 and 2. So 1/4 from 1 is distributed as 1/8 to 3, 1/8 to 2. But it has one incoming edge and that is from 0, which gives it 1/8, half of 1/4. That is 1/8. That is, it gets from node 0. Node 2 has two incoming edges. So one from node 1 and one from node 3. So node 3 gives node 3 has only one outgoing edge, so it gives the entire 1/4 to 2. However, node 1 has two outgoing edges, 1, 8, that is from 1 to 3 and 1 to 2. So it splits 1/4 into two parts. So the resulting is 1/4 into 1, half of 1/4, comes from node 1 and 1/4 comes from node 3. So you get 3/8 in total. And coming to node 3 has two incoming edges. So it gets one from 0 and one from 1, node 1. And from node 0, it gets half of 1/4. And from node 1, it gets half of 1/4. That is 1/4. So now the updated page rank is node 0's page rank remains 1/4. Node 1 has become 1/8. Node 2's has become 3/8 and node 3's has become 1/4. So it remains 1/4. So why are we writing 1/4 is because initially if you see the question, each node's page rank was given as 1/4. So that's why initially everyone's page rank was 1/4 and it was that is how we started the iteration. Okay, so now coming to iteration 2. In iteration 2, we have now again node 0 has one incoming edge that is from node 2. So it gets the entirety of the page rank of node 2, which is 3/8. Node 1 has one incoming edge which is from node 0, so it gets half half of 1/4, which is 1/8. It gets from there. Node 2 has two incoming edges, so it gets 1/4 from node 3 and half of 1/8. So this turns out to be 5/16. And for node 3, it has two incoming edges, so it gets half of 1/4 from node 0 and half of 1/8 from node 1. So that turns out to be 3/16. So this is your x and this is your y. Therefore, z equal to x by y equal to 5/16 over 3/16, that is 5/3. So the right answer for this question is option C, 5/3. All right, so does anyone have a question with the solution? Uh, all right, moving on to question 8. So in a random graph, to visit all nodes in a random walk, the number of nodes required to be traveled is, so with you have n nodes in the graph, so you have to visit all the nodes in a random walk. So again, it's like you have this graph and they are connected somehow, and you decide to do a, a random walk on this graph. So, and what is the uh, number of nodes after which the entire all the nodes would be covered? The right answer is n log n. So it has been empirically found that empirically found that after n log n hops, all the nodes in the graph are covered at least once. So you can generate the entire graph like in a how to collect the web graph. So in n log n steps you can generate the entire graph with its structure with the edges as well. So n log n is the number of hops to the number of nodes required to be traveled is basically the number of hops you have to take to visit all the nodes. So the right answer is option D. Coming to question number 9. So in question 9, in a graph of students with edges representing friendship, choose the correct option based on the two statements. So statement 1 is taking a random walk and dropping one coin to each node while visiting. Students accumulating the most coins will be most popular. And second, giving an equal number of coins to all students at the beginning, and then each student has to distribute them equally to their friends at every snap. After a large number of snaps, the students with the most coins would be most popular. So which of the option is correct? So here popular is equivalent to saying page rank. So it's the same as so higher in a class, the most popular student is equivalent to saying the most popular web page with the highest page rank. So both these definitions, both these methods are give after after large number of iterations. Both methods converge and give the same results. So these are the two methods actually used in for finding page rank. So either you take a random walk in a web graph, that is usually what is done, or you have the web graph already and you distribute points across the edges of the web graph and see which node collects the most number of points. So that is both ways can be used for finding the uh, page rank. So both statements are correct in this case. Coming to question 10. So in question 10, what does teleportation means? Teleportation, so you have choosing a node uniformly at random, creating an edge between two nodes, creating an edge between the highest and lowest rank nodes, changing the leader in a graph manually. So what teleportation does is often used in the page rank algorithm. Used. So let's say you have a network like this. Okay. Something like this. So if you consider this particular node, this particular node has no outlink. So there are three in links but no outlink. So when a page, when you are doing a random walk on the graph and reach a node no outlink. You cannot, from that point and onwards, you can't reach any other node in the graph. So what you do is do teleportation, which is basically pick any random node in graph and restart your PageRank algorithm. So option A is the correct answer. Choosing a node uniformly at random in a graph. Right, so we have discussed the questions of week 6. So now if you have any doubts regarding the solutions that were discussed, you may ask or you may write in the chat box as well. If you have missed any question, I can repeat it as well. So, are there any questions? You can type in the chat box as well if you have any questions. So someone is asking how to calculate the density of communities is basically, so this is not related to this assignment, but for calculating density, you are basically the ratio of the number of edges present within the community and the maximum uh, total number of edges that can exist within the community. So it's basically, so if it's a fully connected network in the community, then the density is 1. If it's not in at all connected, then it is 0, and in between is what you get the density. So ratio of edge node. Okay, so someone is asking how to calculate the iterations. Can you explain again? I think you are referring to uh, this question 7 or question 6. Which one? Can you just um, type which question you are referring to? Okay, question 6. So question 6, it is said that the initial page rank of each of the nodes is 1/4. So what would be the page rank after one iteration? So how do you calculate page rank? So what every node, so page rank, what it does is you take any node, let's say you call that node n v, let's say v. What it does, it equally distributes its existing page rank to its neighbor. So now you have A, B, C, D. So if you look at the page rank of B, so initially it was 1/4. So what B does after one iteration, it gives away. So B gives away to its neighbor. So B has only one neighbor, which is D. So it gives the entire 1/4 to D, but it receives from A and C. So A gives its page rank, divides its page rank equally to B and C gives its entire page rank to B. So B has two components. So it receives half of the page rank of A and the entire page rank of C. So half because A has two neighbors, and the entire from C because C has only one neighbor. So half of 1/4 is 1/8, and from C it receives 1/4. So adding up, B's page rank turns out to be 3/8, and node C receives the entire page rank, so it receives page rank only from A. Now A distributes half to C and half to B, so A is only able to give half of 1/4 to C. So that is why half of 1/4 is uh, given to C, and its page rank becomes 1/8. That is how the page rank is calculated. So in this four options, you calculate page rank for B and C only, but you can similarly you can calculate page rank of A and D as well. I have not shown for A and D because they are not relevant to this answers, but for better explanation, let us try to find out what would be page rank of A. So A receives page rank from uh, D and distributes to B and C. So D gives its entire page rank to A. So it basically it had 1/4 and it gives 1/4 to A. So A's page rank would remain 1/4, and D receives its page rank from B. So it has only one in link, and B gives its entire page rank to D. So D's page rank would also remain 1/4. Or All right. Someone is asking about density of a community with example. So let me try to give you an answer. So yeah, density of a community. So basically, let's say you have 4 nodes in a, this is a community, and you have 4 nodes in the community, and let's say the edges are like this. So number of edges is 3, and maximum number of edges that can exist with 4 nodes is 4 choose 2, which is basically 6, 4 into 3 by 2, that's 6. So density would be 3 over 6, that is half. I hope it is clear. Someone was asking about density. If you have any other questions, you can ask. 4 choose 2 means you have 4 nodes and you are choosing. How do you choose an edge? So basically you pick any 2 nodes, and so total number of edges basically means you, how do you find the total number of edges? You pick any 2 nodes and draw an edge between them. So in a fully connected graph, what you'll do, you'll pick any 2 edge and draw an any 2 nodes and pick and draw an edge between them. So how many ways you can pick 2 nodes from a group of 4 nodes? So 4 is basically your n. So if you have n nodes, how many total number of edges will exist is how many ways you can pick 2 nodes out of the n available nodes. So that would be nc2, n into n minus 1 by 2, n into n minus 1 by 2. Are there any more questions? In tomorrow's lecture, week 7 questions will be discussed. So if you do not have any questions so far, so we can end the session for today and we can meet again next week. So uh, if you have any questions so far, so you can type it in the chat box or unmute yourself and say your doubt. All right, then I think we can close today's session. Thank you everyone for joining in, and all the best for this course. We'll meet again next week at the same time. Bye everyone.